So now that we know what is Laplace transform, we can apply this knowledge to analyze our circuits. And everything that we need to know about how to represent our current sources, voltage sources, our capacitors and inductors, all the essential theory is represented in these two pictures. So it's enough for us to remember this at this beginning stage. Let's say these pictures are taken from a book called Introduction to Electric Circuits, and it's a nice book if you want to practice. And in my opinion, the best way you can learn how to analyze the circuit is by practicing as much as possible. So when it comes to the analysis of a circuit in Laplace domain, we have to take into account two states. So the first state is when our circuit is before time is equal to time zero. So it is called steady state. And in steady state, our circuit has been in this condition for a long time, long enough for the current and for the DC voltage and current to become steady. So it affects how we approximate our voltage, our inductance, and capacitance, because our voltage across the inductor, for example, is equal to inductor multiplied by di dt. But as we know, the DC current does not change, so this thing is essentially equal to zero. The same goes with current across the capacitor. So our current is equal to capacitor multiplied by dV dt, and our voltage in the steady state is steady, so there is no change in voltage, and this is equal to zero as well. So in steady state, the way we represent our circuit is slightly different. So as we know, as we see, there is a switch here, but it is not closed yet, so we still have our resistor. We have our voltage source, we have resistor of 2 ohm, but pay close attention. There is just, let's say, a straight line with no inductor over here. Essentially it is here, but we overlook it for the sake of simplicity in steady state. And over here we have our voltage. And see, I didn't draw any capacitor. Capacitor is in fact still there, but again, this is just an approximation. So when it comes to steady state analysis, we also have to find our initial values. So initial value of current and initial value of our voltage. So this is quite obvious that our V0 is equal to 0, and our I0 is equal to 12 over 4 plus 2, which is equal to 2 ampere. Okay, so now that we know all the initial values, we can move to transient state. And what is transient state? It is a short period when something in your circuit gets disrupted. So as we can see, the switch closes, and now our inductor and capacitor values become important. We can no longer overlook them. So we don't have our resistor value over here. And we have our voltage source. So since we're using Laplace domain, our Laplace representation of the same time domain circuit, we will have 12 over s. Please never forget about this part, because if you do forget, it will cause a lot of mistakes in your calculations. So now we take into account our inductor, and it will be 2s, and we will have our voltage source over here. So this is taken by multiplying inductor by our initial value of current. Here we will have our capacitor value, which is equal to 1 not 1, 8 over S, which is just 1 over capacitor multiplied by S. And we don't have any voltage source over here because our initial voltage is equal to 0. So in this case, in my opinion, it's easier to use node voltage method. You can as well use mesh current. So here we just take voltage at node A and write that equation is equal to 0. So here is our ground, okay? This becomes very simple. Now the problem is very simple because we have all the essential information over here. And the rest is just pure calculation. So this will be VA over 2 minus 6S plus VA over 2S plus 2 over S plus VAS over 8. So VA can be taken out of the brackets and we will have it equal to 4S. So VA will be equal to 4S over this whole thing, which is equal to 32 over S plus 2 if you calculate it. So this is the representation of VA in S domain. But if we want to convert it to time domain, we will have, so this is S domain, this is time domain. We will have 32 multiplied by Euler's number to the power of minus 2t to account for that shift multiplied by t. And this VA is also a voltage drop across the capacitor. So the next example is slightly more involving. We know our initial voltage value, initial voltage equation, and we have to find capacitance value C. We apply all the same methods. So first we have to find our I0 and V0. The switch is not yet closed, so we have our resistor, we have our voltage source, we have 2 here and 4 over here. We overlook our capacitor for a while and just draw the V0 of t. So here, as we can see, there is no I of t, so we can forget about the initial value of I, and all that we have to find is the initial value of our voltage, and initial value of our voltage is just the voltage drop across our resistor. So for that I can use voltage divider rule multiplied by 24, and as a result I will get that my V0 is equal to 4 volts. Now I can move on and analyze my circuits in transient state. So the switch is closed and there is no more resistor. Our voltage source, and here, careful, we have to account for the capacitance values plus the voltage source. Okay, so this can be solved using mesh current methods, I1 and I2, and this becomes rather simple because it's just a set of linear equations. So it will be minus 24 over S plus 4 I1 minus I2 plus 2I1 is equal to 0, and 4 I2 minus I1 plus 1 over CS plus 4S. So first, I like to find what is I1 is equal to. So I'll first solve this thing. So 4i1 minus 4i2 plus 2i1 minus 24 over s is equal to 0. So from this, I can say that I1 is equal to 2i2 over 3 plus 4s. This is the first set of equations. This is the first set. This is the first equation, and this is the second equation. So now that I know what is I1 is equal to, I can solve this second equation and find what is I2 is equal to. So I2, 4i2 minus 4i1 plus 1 over cs plus 4s is equal to 0. And here I can just substitute and as a result, you can solve this set of equations yourself, and you will find that I2 is equal to 12 over s over 4 over 3 plus 1 of cs. Okay, and as a result, we get 36c over 4cs plus 3. This is our I2. And they are asking for the capacitance value. So in order to find our capacitance, we can find the voltage drop of our capacitor. So the voltage drop across the capacitor C will be equal to 1 over cs multiplied by I2 plus 4s, 4 over s. And this is also equal to this thing, right? So if we represent V0 in the S domain, we will get 16 over s minus 12 s plus 0.6. So this whole thing is equal to 16 over s minus blah blah blah. So we substitute the value of I2. And first of all, I like to just simplify this guy over here. So this can be simplified as A over S plus B over 4CS plus 3. Okay, and if you actually solve that, you will get that A is equal to 16 and our B is equal to minus 48C. Okay, and we can see that this thing is equal to this thing over here, which means that we are in the right direction. So all that is left is we have to solve this part and equate it to minus 12 over C plus 0.6 from the initial condition. Okay, and if you actually solve that, you will get that your capacitor value is equal to 1.25 farads. So I hope that you find this video helpful. Thank you for watching.